Hi dears, today we can see MCQ part 3 for algebra. So the first question, let R and R dash be two arbitrary rings. Pi from R to R dash defined as pi of A equal to 0 for all A belongs to R. Then pi is a homomorphism. That's the right answer. If pi A is equal to 0, then pi is a homomorphism. The second one, the homomorphism pi of rings R into R dash is an isomorphism. If and only if the kernel I of pi is equal to 0 ideal is the right. The kernel whose maps to the 0 ideal, then we can say the homomorphism become the isomorphism. Third question, let R be a ring. U not equal to empty subset of R is said to be ideal of R. Then the first condition, U is a subgroup of R under addition, and the second condition, for all U belongs to U, R belongs to R, RU and UR belongs to U. So out of these four, which are the conditions satisfied for this ideal? So these two conditions also satisfied for the ideal. This is the definition of ideal. So U not equal to pi, it satisfies U is a subgroup of R under addition, and RU, UR belongs to U. So A and B are true. Now, the fourth one, if U is an ideal of ring R, then U by R is a ring is the right answer. That is, U is an ideal and R is a ring. So, ideal by a ring gives a ring. So, U by R is a ring. If integral domain D is of finite characteristic, then its characteristics is a prime number. So finite characteristics means MA equal to 0 with A not equal to 0 gives M equal to 0 is the condition for finite characteristics. So if it is an integral domain, then its characteristics is a prime number. Sixth question. If R is a commutative ring with unit element and M is a maximal ideal, if it's so, R by M is a field. R is a ring, commutative ring, and M is the ideal, that is a maximal ideal, then we can say R by M is a field. In the previous question we see ideal divides a ring, this gives a ring. Here a ring divides, that is commutative ring, divides ideal, which is maximal, it gives field. And this question is asked in 7th one with slight difference. Here you can see that R is a commutative ring with unit element and M is an ideal. R by M is a finite integral domain. Then which of the option is right? So the same question we see there. M is a maximal ideal of R. So R is a commutative ring with unit element and M, that is a maximal ideal. The last we see which implies field. And again we know that finite integral domain is field. So using that condition we can say that M is a maximal ideal of R. Now the eighth one, if R is a Euclidean ring and A comma B belongs to R and B not equal to 0 is not a unit in R, then the option D of A less than D of AB is right. R is a Euclidean ring. Now the ninth question, if pi is a prime element in Euclidean ring and pi divides AB, then pi does not divide A or pi does not divide B. Pi does not divide A and pi does not divide B. Out of these two, this is the right option. Pi does not divide A or pi does not divide B. The next question, if fx and gx are polynomials out of which degree of fx into gx is greater than or equal to a degree of f of x with g of x not equal to 0 is the right. So this was greater than or equal to is right. And you can see the third option, degree fx into gx is equal to degree fx into gx is the wrong. If it is degree fx plus degree gx, then this is also the right option. So if fx and gx are the non-zero polynomials, then these two conditions are satisfied. If I am putting here plus, then these two conditions are satisfied. Now the 11th question. Given a polynomial fx is equal to a0 plus a1x etc. plus an exponent, and these ai's are integers, then the content is the GCD of the integers. So that is the content. And if the question is fx is a polynomial, then what about the primitive polynomial? Primitive polynomial is the GCD of the integers a0, a1, etc., an equal to 1, then that polynomial is said to be primitive polynomial. The content means just the GCD of the integers. 12th question. If R is a commutative ring with a unit element, then the option A is right. Every maximal ideal is prime ideal. Maximal ideal is prime ideal for the ring, commutative ring with unit element. The same question, 12th question. Here you can see the condition. If R is finite and commutative ring with unit element, then the option is every prime ideal is a maximal ideal. See this difference. R is a commutative ring with unit element. The maximal ideal implies prime ideal. If it is finite, the prime ideal implies maximal ideal. Then the 14th one, an integer polynomial, integer monic polynomial is a. It is a primitive polynomial. So integer monic polynomial means the coefficients are integers and the highest coefficient is 1. For the monic polynomial, highest coefficient is 1. Also, all the coefficients are integers. Right? If it's so, then we can say that integer monic polynomial. And the integer monic polynomial is a primitive polynomial. So that's nothing but the GCD of all the integers are equal to 1. And similarly, primitive polynomial, you can say that if fx and gx are the primitive polynomial, then multiplication is possible. That is, f of x into g of x is a primitive polynomial, but f plus or minus is not a primitive polynomial, and the quotient is also not a primitive polynomial. So if two polynomials is there, then the multiplication alone be the primitive polynomial. Now the 15th question. Which of the following statement is false? Fx. This represents the field of polynomials where the coefficients over the field f. So fx represents the field of polynomials with coefficients are over the field f. So this represents fx. So fx is an integral domain. Fx, the question is which of the following is false? So integral domain PIR, that is principal ideal ring, then Euclidean ring, and D is fx is not a group. So this is false because already we seen that field. Field is an integral domain that we seen. Again, field is, every field is a ring and every ring is a group. So definitely we can say that field is a group. So here it is not a group. So that is the wrong option. Then the 16th one, if R is an integral domain, then Rx is an integral domain. Other three options are a wrong option. So Rx is not an integral option, is wrong. Rx is a commutative division ring, wrong option, and Rx is a field to also a wrong. So Rx is an integral domain. That means the ring of polynomials, R represent ring of polynomials in which the coefficients are over R. So R is an integral domain. R of x is also an integral domain. Thank you.